Hello. All right, another lecture where I assume you have seen all of this before, so I will go quickly through this stuff. But again, our goal is to describe objects moving as a function of time. We want to ultimately describe objects moving through physical space. To do that, we need some sort of agreed upon system that allows us to describe properties of this motion in terms of things like position, velocity, acceleration, momentum, energy, mass can play a role as well, angular momentum, pressure, right? If we want to describe dynamical systems and trajectories, there are a variety of different things that arise that we need in order to properly describe this motion. Some of these quantities are scalar functions, or scalars, while others are vectors. Two words you have definitely seen before, but let's remind ourselves. Scalars: mass, energy, pressure, examples of quantities that lack directionality. I cannot tell you which way mass points. There's no direction associated with mass or energy or something like pressure. You might think with pressure, actually, that there might be some directionality with pressure when you think of like high pressure and low pressure friends with weather, but it turns out it's the gradient or the change in pressure that really has, meaning there. That is a vector, but pressure itself, not a vector, just a scalar. What this means is you don't need to impose a coordinate system. These do not need coordinate systems to describe. I do not need to lay down an axis to talk about mass, or said another way, and actually a way that scalars are typically defined, is that any coordinate system agrees upon the values of things like mass and energy, for example. It is not dependent on the coordinate system in order to uniquely define these sorts of values. Where vectors, on the other hand, are both a magnitude and a direction. It has some sort of size, and there's directionality associated with it. In this case, you need a coordinate system to properly define. So, what does it mean to be a coordinate system? A coordinate system has an origin, something that specifies kind of the 0 point of a coordinate system, along various axes. These axes, if you think of this in terms of directions, might be directional axes, for example. Ideally, these axes are chosen to be perpendicular axes, or perpendicular to each other. They don't have to be. So life gets a lot simpler when they are. Another word to say this is that they're orthogonal to one another. Orthogonal just being a fancy word for perpendicular. And actually the word perpendicular itself is a more sophisticated statement than you might think, but your intuition about what perpendicular means in terms of a physical sense, in terms of a physical kind of relationship sense, 90-degree angles, will be just fine for right now. Oops. Ugh. This double tap is a blessing and a curse to turn the pen into an eraser. Orthogonal axes are typically used. The most kind of common and example you're most familiar with is, of course, the Cartesian axes. Cartesian axis, which in 3 dimensions has an origin that might specify 0, 0, 0, and then there is an x direction, a y direction, and a z direction, with each of these axes being perpendicular to one another. They all make 90-degree angles with one another. Such that if I want to define the location of a point P from the origin, it can be described as some distance along each of these perpendicular axes, which might trace out kind of a parallelogram of sorts. Where it moves some direction out in the x direction, some position out in the y direction, and some distance out in the z direction as well. So I could write the position of this object as maybe x, comma y, comma z, depending on, and those might have certain values. Right, example 1, comma 2, comma -2 meters might be one example of a position vector. You go 1 meter out in the x direction, 2 meters out in the y direction, -2 meters out in the z direction, which just means I go in the opposite direction as what my axes define as the positive direction. Right, notice that I drew this little arrow here that tells you the direction. Really, it's just saying you're making a decision about what direction is positive and which direction is negative. There's nothing inherently different about the negative side compared to the positive side. It's just giving you a sense of directionality along each of the axes. So what I've drawn here might be an example of how you write down a vector. I've kind of used the bracket notation or the bracket notation, where my coordinates are kind of listed within the brackets. There are other ways that it's written down that you've seen. It can be written down in terms of, say, x. Then you can use unit vectors, which we'll come back to in a second, where you use kind of the chevron hat notation of just how much in the x direction, how much in the y direction, how much in the z direction. Engineering notation uses I, j, and k instead. Or you might see it as kind of a column vector where you might have x, comma y, comma z, but all written kind of vertically instead, and kind of in this case, kind of a very simple matrix that has 3 rows and 1 column. All equivalent ways of writing down a vector that specifies some sort of directionality associated with that vector as well. As compared to, say, mass, if I say the mass is 2 kilograms, I can just write down m equals 2 kilograms. I don't have to associate any sort of directionality with it because it is a scalar, not a vector. No, in this case of the vector, since in this case I'm drawing it relative to an origin, if I were to put my origin somewhere else, or if I were to orient the axes in different directions, the vector would change. Of course, something like mass does not care what these axes are and how they're oriented. And jumping ahead, Again, assuming you've seen all this before, so I can jump around before I define terms properly. The coordinate systems, so ideally I said that the coordinate systems are orthogonal. And we can say that they're cyclic in that they obey the right-hand rule. As well. And by that I mean that if you look at the axes, the cross products of the axes all have, the cross product of two axes gives you the third axis. So there's an ordering associated with it. When I say x, y, z, and I wrote x, y, z here in a very particular way, let me recopy it because that's getting kind of busy. Right, z up, y to the right, and x kind of in and out of the page perhaps. Where notice that the cross product of x cross y, which you can remember, I put my right hand out in the direction of x, I move my fingers so that they point in the direction of y, and then my thumb points in the resulting direction of the resulting vector, which notice, if you do that, is z. But then if I go next, y cross z, notice I get x. And then z cross x, notice I get y. So these are cyclic coordinates as well, and that they're ordered and arranged such that they obey the right-hand rule, which can be helpful, especially when we deal with things like rotation and whatnot. So, coordinate systems need an origin and some sort of directionality along the axes, both of which you are free to determine and make whatever you feel is most useful for the problem. The coordinate system and what you make of it is something you're allowed to choose and decide upon, as well as the kind of axes you're going to use. Right, this was an example of Cartesian coordinates. I go back to writing this just as 2D, right? This is x and this is y. The Cartesian axes, like the ones I've drawn, are nice in that they remain fixed as a particle moves around the axis, or around the physical space, in this case the 2D physical space of the piece of paper. The axes themselves do not move. Y is always up. The positive direction of y is always up, or in the positive direction of x is always to the right. That can be contrasted. So for example, if I have a particle p here, right, I can specify where it is on the y-axis and where it is on the x-axis. And then if the particle moves over here, I can specify where it is along the same exact axes, which the x and y values will have changed. This is different for, say, something like a cylindrical coordinate system or a spherical coordinate system, where cylindrical might look at this point here, and it will associate axes where it has one of them pointing radially away from the origin, and then it will come up with a perpendicular one that's perpendicular and call that the theta direction. And why this is different, you might think it just kind of looks like the Cartesian coordinate axis rotated a little bit. And more or less, it is. But the thing that's different about the cylindrical coordinate axes, which we'll come back to later on, is that as the particle moves, say over to here, the axes move with it as well. So then, in this case, once the particle moves to the second spot, this corresponds to the direction in the positive direction of the radial axis. And then this corresponds to the positive direction of the cylindrical axis. Again, with them being perpendicular to one another, though I did not draw them very well to be perpendicular. But in that case, the axes themselves also are moving around as the particle moves around, which is different than the Cartesian axes, which they're kind of fixed and things kind of move around the fixed axis. Here, with cylindrical, the axes rotate along with the object. So you can always talk about how far away radially it is from the origin, and then there's the perpendicular component, or you might call that the tangential component. Then cylindrical can have a third dimension, kind of in and out of the page, the z component, or you can have a third component that not only in this case theta, if you look at theta, it's kind of rotating around the xy origin. You can also have a third dimension that kind of rotates around the xz origin, if you imagine z coming in and out of the page, and we call that a spherical coordinate system as well. But we'll come back to those. But these are examples of different kinds of coordinate systems that all are specified by an origin and perpendicular axes. Let's stick with Cartesian for now. So again, x, y. I have my origin here. The arrows are kind of specifying which directions I associate with positive. Again, something you are free to determine and choose for whatever problem you're doing. Let me specify a vector. If I really were to define a vector is a directed line segment that has some length in each of the appropriate axes. In this case, I'm dealing with 2D. If it was 3D, I could have a delta z as well. So this arrow here, I don't know, I'll call it v. This vector v can be defined as delta x comma delta y. It has some sort of length in the x direction and some sort of length in the y direction. And again, if I wanted to do engineering notation, I could do something like this. Or I could write it as a column vector, whichever way you like. Now I could also take this vector, make a copy of it, and move it over here. In which case it has, again, the exact same delta y, but now it's starting and ending in a different spot, and the exact same delta x, but again, it's starting and ending at a different spot. These two vectors are identical. A vector is not anchored to an origin. The vector is just a directed line segment that has some length in each of the perpendicular axes. Sometimes it is useful to interpret a vector as always emerging from the origin. Position is one of these vectors, where if you have a coordinate system that defines an origin, that kind of specifies, where you find to be home base or whatever it's going to be in that coordinate system. And then position, if I tell you my position is 1, 2, 3, that tells me relative to your specified origin where to find the particle or mass or box or whatever it is that's moving around. But vectors by definition really don't require a coordinate system, though in physics we often like to interpret them relative to some sort of coordinate system. So to give just another example, though again I imagine this is all old news. If I were dealing with, say, uniform circular motion, I might have a particle that's located here from my specified origin with these two axes I've defined. And I might write that there's an arrow, a vector here that corresponds to the position vector. It might have some velocity, maybe it's moving clockwise, so it might have some velocity that is moving in that direction. And then it's also experiencing an acceleration towards the center. So it might have an acceleration vector that is the blue arrow here. I've drawn it kind of relative to the particle itself, which is kind of nice in physics, right? There's a velocity that's associated with that particle. That velocity v tells me where in the coordinate system and how fast the object is moving. The acceleration is telling me something about how that velocity vector is changing, and the position vector is telling me where the object is relative to the origin. But again, vectors are just line segments. So the information on the left-hand side is exactly the same as what I'm drawing here on the left or the right-hand side, where I'm having them all originate from the origin. Again, it's the directionality by their length and direction that really is what the vector is saying. Whether or not you put them at the particle or from the origin is up to you. Again, unless it's a vector where assuming it's originating from the origin is kind of built into the definition, like, for example, position, or absolute position, let's say. Relative position, Obviously, that doesn't need to be originating or always beginning at the origin. So, the usual properties of vectors. That suppose I have, suppose I have a vector A, call it this. Then I also have a vector B, let's call it this. I could ask myself, what is the vector C, which is A plus B? Right, maybe both these vectors is, I first start by walking from my house in direction A, or distance A, and then I change direction and walk for a distance in the direction defined by B. Where do I ultimately end up? Well, again, since I don't need to anchor the vectors to the origin, I can make a copy of B here, and then C, being the vector A plus the vector B, is then just the vector sum of the two. So then C in this case is just, I walk out A, and then once I get to the end of A, I rotate and turn and walk in the direction defined by B, based on the length given by the vector B. My ultimate location is the vector C. I think it was called the parallelogram rule or something like that. If I want to say, if I'm walking in the direction A, and I want to say, what does the vector correspond to half that distance in the same direction, right? I might draw that vector as something like this. And again, I can define that as 1/2 kind of times the vector A. It is something that is half as long as vector A, but points in the same direction as A. So this is working in scalars. And then finally, if instead of moving in the direction and length of B, I move the same amount of distance, but in the opposite direction, right? I might draw that as something like this, and I might call that negative B. Right? It is in the opposite direction of B, hence the negative sign, but it's the same distance as B. These are all, again, I didn't need to define a coordinate system in order to write down everything I just did. But if I do define a coordinate system, the nice thing about this is that for vector addition and subtraction and scalar multiplication, I can do it component by component. So suppose A is 2, 1, 2 in the x direction, 1 in the y direction. Then B is 1, 3, 1 in the x direction, 3 in the y direction. The vector sum then is just the sum of the x components plus the sum of the y components. So it would be 3, 4 in that case. Ultimately, 3 in the x direction, 4 in the y direction. Scalar multiplication, when I multiply a vector by a scalar, just a number, the 1/2 is just a number, I can multiply each component by that scalar. So instead of 2, 1, it becomes 2 divided by 2, and then 1 divided by 2, or 1, 1/2. Similarly, negative B, I can think of that as just the scalar -1 times the vector B. So then I can think of that as -1, -3. Go to the usual stuff. Subtraction, right? What about A minus B? Well, again, I can think of that as A plus -1 B. So we already figured that out. It looks like A was 2, 1 plus negative B, which we wrote down as -1, -3. And so that looks like at the end of the day, it's 1, -2 as a result. The subtraction of two vectors comes up a lot when you want to think about, say, relative positions. And this parallelogram rule of how you add vectors together can be very helpful in kind of visualizing this. Well, again, I think we've all seen this before. A goal for these next few lectures is to get a better geometric appreciation for vectors and how to reason what we're seeing when we draw vectors and do vector operations. So suppose I have a particle that's located here, call that particle 1. And then suppose I have another particle that's located here, call that particle 2. And it has some positions that are given by, say, A and B. It might be that I'm curious and asking, for example, what is the relative distance between them? Or if I'm located at particle 1 and I want to walk to particle 2, which direction should I turn and how far should I walk? Now A and B are telling us where the positions of those two particles are from the origin, but those are not saying, at least individually, how particle 1 and particle 2 are located relative to one another. Really, what I'm asking for is what is this vector here, C, where it's telling me the distance in between them and the direction I need to go if I want to, say, go from particle 1 to particle 2. So how can I figure out C based on A and B? Well, notice that there are two ways that you can get to particle 2. One of them is to just start at the origin and go out to particle 2. That's just B. The other is to start at the origin, go out to particle 1, and then once you're at particle 1, go out to particle 2. Well, if I look at the vectors, that looks like it's just A plus C in that case. So in both cases, I started at the origin and then I ended up at the same spot. These are identical expressions in terms of vector addition. And so C then is simply just B minus A in this case. That would tell me both the direction of how I get from particle 1 to particle 2, and it would tell me the length or the relative distance between them if I looked at how long that arrow was. Gravity is one example where this is relevant, right? GMM over d squared, there are two particles, and you care about the relative distance in between them. And if they're both not at the origin, then you have to figure out kind of what that relative distance is in between them, which this sort of thing can be used to figure that out. Right? Just to kind of give a general example, right? If I have particle alpha here and particle beta here, again, you can specify the position of alpha, the position of beta as vectors. But then this vector here, this relative vector, R, I can define that based on what I just, this is supposed to be a beta. That looks like it's just R beta minus R alpha in this case. And so a good thing to remember when you have an expression like this, or like this, and we have the difference of two vectors, you'll often be wondering what direction does this C point in, or what this vector R points in. Does it point from A to B, or does it point from B to A? Or in the case of R, is it pointing from alpha to beta or from beta to alpha? Now, of course, you could always just draw a diagram. And I would say do that until this really becomes very intuitive. But the way I remember it, when I have the difference of two vectors, I think of it as points to B from A. And I just have done this enough that I've just committed that to memory. When I have B minus A, that's a vector that points to B from A. For R equals R beta minus R alpha, that points to beta from alpha. Just remember, to the first one from the last one, when you have the difference of two vectors. All right. So that's kind of the basics. Again, I feel like we've seen this before. And then various fun mathematical properties of vectors, right? Vector addition is associative. So right, A plus B, all in parentheses, plus C is the same thing as A plus B plus C in parentheses. Essentially, order doesn't matter for addition, does for subtraction. Of course, I got to be careful with order of operations. It's commutative, A plus B is the same thing as B plus A. Scalar multiplication distributes, right? Some constant A multiplied by two vectors is the same thing as if the constant distributes. Again, these are all things where you can, using the axes notation, where you could prove this for yourself, or draw pictures and convince yourself geometrically that this is true. Derivatives also distribute as well, right? Derivative A plus B is the derivative of A plus derivative B for vectors as well. But I'm saving calculus stuff for a different module. So all good stuff we've seen before. Now, while a scalar is defined as a magnitude with no directionality, a vector is defined as having both a magnitude or a length plus a direction. We've just talked about how these arrows are kind of specifying directionality. But again, let's really zoom in on that idea. The magnitude of a vector, we can think of as the length of a vector. It's just asking how long the vector is. So if I have some sort of line segment here, that corresponds to my vector A, which has some length delta x in the x direction, and delta y in the y direction. I can specify that vector as delta x comma delta y. And if I want to ask how long that vector is, this introduces kind of a good mantra for a course like this is to always look for triangles. So notice that it goes over delta x in the x direction, delta y in the vertical direction, and I'm curious to know how long that black line segment is, but lo and behold, that looks like it's just the hypotenuse of a right triangle. So I can define the magnitude of a vector, which I'll specify either as writing A without a little arrow, or A kind of in kind of absolute value signs there. If it's just the length of that vector, then by the Pythagorean theorem, looks like it's just going to be that in this case. And then this generalizes to in n dimensions. The Pythagorean theorem actually can be generalized to the same sort of thing in n dimensions. So the length of a vector r, right, might be delta x squared plus delta y squared plus delta z squared in three dimensions. My hand is very shaky today, I'm sorry. In n dimensions, you could write this as the sum of the delta x sub i's, and then that's all in the square root. All right, so it might be delta x squared plus delta y squared plus delta z squared plus delta w squared plus delta alpha squared, whatever your axis labels are, just keeps on going, where I'm using kind of summation notation where I might start from going from 1 to however many n dimensions there are in that case. All right, good. We've seen that before. So that tells me how long the vector is, the magnitude of a vector. But if a vector is both length and direction, length we can call the magnitude. Direction, we might, is there something I can kind of, when I look at a vector, is there something that just associates to me the direction of the vector? Well, I can write down a unit vector. And this is a vector, so it does have directionality associated with it. I'll write it as u. No, never mind. Oh, this double tap is killing me. Vector, I'll write it as A with a little chevron instead of an arrow. That is a vector, because that's redundant with what I just said. And also, the magnitude of the vector is unity. So something that is a vector, but has magnitude equal to 1 in this case. And this kind of is the component that associates the directionality of the vector. So before I was kind of defining the axes in terms of x hat and y hat. I can think of x hat as just 1, 0, and then y hat as 0, 1 in 2D. If it was 3D, 1, 0, 0, 0, 1, 0. Then you could have a z hat that's 0, 0, 1. And then notice that the magnitude of this vector then is going to be the square root of 1 squared plus 0 squared, which is 1. Similarly, this has unit length. So these are unit vectors that are really just saying something about directionality. What about a more general vector? Suppose I have a vector that's 1, 1. So this might be something that points at a 45-degree angle and has unit length along each axis. Now the magnitude of this vector, I can easily figure out, is going to be 1 squared plus 1 squared all in the square root, or a square root of 2, which is not equal to 1. So this vector on its own is not a unit vector. I could ask if I could figure out how to turn this into a unit vector such that I could come up with r hat such that it is pointing in the same direction as r, but has unit length. You can imagine that I know how to multiply by scalars, so I could just scale the entire vector down by an amount such that its length becomes unity. So I might write this as the original vector divided by its magnitude. So in that case, it would be 1, square root of 2, 1 over the square root of 2, 1 over the square root of 2. And you notice, unsurprisingly, that the magnitude of r hat then is 1 over the square root of 2 squared plus 1 over the square root of 2 squared, which is 1. So this is a unit vector version of r, where, going back up to this diagram, if that is the direction of r, this might be r hat. Something that points in the exact same direction or is parallel to the original vector, but the length has been scaled such that it has unit length. So this here is kind of an important relationship, because it is both defining what a unit vector is, and also I think really geometrically is saying something about vectors and how they are both magnitude and direction. Because if I take this expression and rewrite it as r vector, that then looks like it's the magnitude of r times r hat. Which, if I look at this, the magnitude of the original vector, that is the magnitude or the length, times r hat, which is the direction of that vector. Which is the definition of a vector. It has both a magnitude and a direction. So you can write any vector as its magnitude times a unit vector that points in the direction of the original vector. And you can figure out, and if you have an axis, you can define components that define each of the components of that vector as well. All right. I guess let me just say that sometimes just a notation thing. I forget which of these your book uses, is that we might be interested in doing summations or having some sort of index, or dealing with kind of index notation. For vectors, where, oh, and I'm out of room. Come on. All right, if A is something like x comma y comma z, which I can write as x in the I direction plus y in the j direction plus z in the k direction, or I can write it as x comma y comma z as a column vector. Sometimes I might want to be more general, right? Rather than saying x, y, z, or having to assign unique symbols to each axis, I might want to have kind of one symbol that has an index that is associated with, x, y, and z. Thinking of this as in terms of programming, right? You don't want to define a variable for x, a variable for y, a variable for z. Or at least it's not very efficient, especially if you want to make use of things like NumPy vector operations. You want instead to have some sort of column or list where you associate the first entry with x, the second entry with y, the third entry z, and then if you wanted to have 10 dimensions, right, you just have a 10 element list, or whatever you need. So you might see it written as kind of x, and then rather than x hat, y hat, and z hat, I might use e1 hat plus y e2 hat plus z e3 hat. Where notice I'm using the same symbol throughout, just the only thing that differs is kind of the subscript, which is going to be 1, 2, and 3 for 3 dimensions. I can just do 1 and 2 for 2 dimensions, or go out to how many ever I want. Or again, if you want to think programming-wise, where most programming languages start at 0, or you can think E0, E1, E2 could be X, Y, and Z, for example. That makes it a little bit more compact, because then I could write A as, right, which might have components kind of A sub I, A sub j, A sub k, or A1 in the x direction, A2 in the y direction, A3 in the z direction. I might want to write that instead as kind of A sub I, E sub I, and then I'm summing over all three, right? It's the term associated with x, which is a vector component, plus the component associated with y, plus the component associated with z, right? So E, right, the x direction, the y direction, the z direction. And I'm using Cartesian axes of x, y, and z, but these don't have to be necessarily Cartesian, right? Again, we talked about cylindrical and spherical coordinate systems, which are really something we see, right? I could have E1, E2, and E3 correspond to the radial, the tangential, and the z direction for cylindrical coordinate systems, or the radial, the azimuthal, and the altitude, and axes for spherical coordinates. So these are things we'll see, and these are all just kind of equivalent ways of writing down the exact same thing. So again, I assume most of that was review, and then we'll build on to dot products and curl, not curl, cross products, dot products and cross products next time.